Hi and welcome. We are going to look at the goodness of fit and how to do some of the computations by hand, and then we're also going to look at how to do some of those computations using StatCrunch. First thing though, what does it mean when it says we're going to test for goodness of fit? So what we have to do is we have to try to determine, using a hypothesis test, if the frequencies from a sample match or agree with some predetermined distribution. Now, the predetermined distribution, it might be a normal distribution. It could be a uniform distribution. It could be something like what's known as Benford's law, or it could be something else. So the predetermined distribution has a variety of different options that it could take. Now, this is a hypothesis test, so we are going to start with the requirements. And our first requirement is that our sample has to be a random sample. We also want to make sure that our sample consists of frequency counts for each category. And then this last one is a little bit abstract. It says for each category, the expected frequency, not the observed frequency, but the expected frequency is at least 5. So this one can throw people off sometimes. So let's say that we have 4 different categories. We're just going to call it A, B, C, and D. And let's say our predetermined distribution says that 2/5 of our observations should come from A, 1/10 should come from B, 3/10 should come from C, and 1/5 should come from D. Now, if we have a sample size of 10, well, we need to figure out for our expected amount what would be expected for each of these categories, and we're going to just use a capital E to represent that. Well, in order to figure out my expected value, I would take 2/5 of 10, because 2/5 of my 10 items should go to category A. Well, when I do 2/5 of 10, I end up getting 4. So I would expect that 4 out of my 10 would be in category A. Well, right there, we've actually already violated this last requirement that says for each category, the expected frequency is at least 5. So we would not necessarily want to continue if our sample size was only 10. Now, let's change that up a little bit. Let's say that instead, our sample size was, let's say, 80. Well, I would need to go through and compute the expected value for each of these. So I would start by doing 2/5 of 80, and that's going to give me 64. Then I would need to do 1/10 of 80, and that's going to give me 8. And then 3/10 of 80 is going to give me 24, and then 1/5 of 80 should give me 32. Now, when I look at my expected values here, all of them were at least 5. So if my sample size were 80, I have this requirement meant that the expected frequencies be at least 5. Now, when we get into doing our hypothesis test, we want to start with our null and our alternative hypothesis, like we do for any of our tests. Now, in this case, my null hypothesis is going to be some form of phrasing that the observed frequencies agree with the claimed distribution. Now, this is not going to be the only phrasing that you see, but it will have that general idea that our observations agree with what's expected. Our alternative hypothesis is going to be that at least one of the observed frequencies is different. So it's not that all of them are different, it's just that at least one of them. And once we get our null and our alternative hypothesis set up, we would compute our test statistic. Now, a goodness of fit test is always going to be a right-tailed chi-squared test. To compute our test statistic, we have our chi-squared value is equal to the summation, and this capital O here stands for observed values, and the E stands for the expected values. So we would take each of our observed minus its expected value, and then we would square that, each of those, divide them by their expected value, and then take the sum of all those, and that would give us our test statistic. Once we have our test statistic, we can either use the critical value method, where we would use the standard chi-square table, and then our degrees of freedom would be k minus 1, where k is the number of categories. Or we could use the p-value method, which typically we would use technology to compute that for the p-value method. So we're going to first look at how could we calculate the test statistic if we are interested in equally likely outcomes. Now, when we see the phrase equally likely, that's an indication that we are looking at a uniform distribution. Uniform meaning it's equal. So we think that each of the categories should have the same number of items in there. So our example we're going to use, it says, let's test the claim at 0.05 significance level that all the colors of Skittles are evenly distributed. I used 8 bags of Skittles, which came to a total of 468 Skittles. There were 88 reds, 94 oranges, 93 yellow, 96 green, and 97 purple. So, first thing I need to do is check my requirements. So I need to decide, was this a random sample? Well, it doesn't really give us any indication that it was not a random sample, so we're going to assume that the 8 bags of Skittles were just random bags and that there was nothing particularly special about them that allowed them to be picked. Then the second thing, we have to have frequency counts for each of our categories, which we do. We have a frequency of 88 for red, 94 for orange, etc., etc. And then the third thing is that the expected frequency for each category is at least 5. So I'm going to go ahead and set up my my categories here. So I'm just going to use red, orange, yellow, green, and purple. Now, unlike our previous one where it gave us a particular fraction, we don't have that in this case because it says we have a uniform distribution. So what you have to realize is that each of these categories should have the same expected amount. Now, since we have 5 categories and we essentially want 100% of our data to be represented, we would need to take our 100% divided by 5, and that's going to give us 20%. So it tells us that 20% of our values should be in each category. Well, 20% is really the decimal point 2. So when I come over here to compute my expected frequency for each category, I'm going to take that 0.2 and I'm going to multiply it by my 468 Skittles. So I know how many Skittles should I expect to be in the red category. When I do that computation, I get 93.6. Now, because this is a uniform distribution, I'm going to end up with the exact same thing in every single category. So all of these are going to turn out to be 93.6. Now, to check my requirement, it says that my expected frequency needs to be at least 5 for every category. Well, we have definitely satisfied that because 93.6 is larger than 5 for each category. Now that we've checked all our requirements, we can set up our null and our alternative hypothesis. So my null hypothesis would be that the proportion of red is equal to the proportion of orange equals proportion of yellow equals the proportion of green equals the proportion of blue equals the proportion of purple. Or we might just write it as a sentence that all the colors are equally distributed. My alternative hypothesis would be at least one of the proportions is different from the others. So now we're going to go and we are going to compute the test statistic. Now to do our test statistic, we need to take our observed minus our expected values. So I'm going to go ahead and transfer my information into kind of a table. And I'm going to put my categories over here: red, orange, yellow, green, no, not blue, purple. Now, my observed values, that's going to be the information from the problem. So my observed number of reds was 88. My observed number of orange was 94. My yellows, there were 93. My greens, there were 96. And my purple, there were 97. Now my expected value, that was what we had already computed when we were checking the requirements. So my expected value for each of these was 93.6. And because this was a uniform distribution, it was 93.6 for every single category. Now, when I look at my formula, it says I need to do the observed minus the expected. So I'm going to just make another column of the observed minus the expected. And for my red category, I would then take 88 minus the 93.6, and that's going to give me a negative 5.6. I'm going to do that for every single one of my categories. So oranges, I'm going to take 94 minus the 93.6. And I'm going to record all of those values in my table. Alright, so now I have all of my differences recorded here. It says the next thing I need to do is I need to take my observed minus my expected, and I need to square each of those values. So now I'm going to have to go back to my column here with my observed minus my expected, and I'm going to square each of those values. So when I do my negative 5.6, I end up getting 31.36. Now at this point, because we're squaring, there should be no negatives left in your answers because a negative times a negative is a positive. So there I have all my squared values. So I have my observed minus my expected. I squared them. Now the last thing I need to do here is divide those by E. So I'm going to take my observed minus expected squared, the column I just did, divide it by the expected values. I'm going to get my expected values again from my column over there titled E. So for this first one, I would take my 31.36 divided by 93.6. When I do that, I end up getting 0.335. So I'm going to do that for each of my values now. So there I have all of my values when I took my observed minus expected squared value and I divided it by the expected value. Now I have the summation symbol out front here, which means I need to find the sum of that last column. So I would need to add up all of my values there, and then that's going to be my test statistic. So when I added them all up, I got 0.5256. So I now have that my test statistic, my chi-squared value, is 0.5256 for this particular data set. Now, keep in mind, when we're doing this chi-squared test for goodness of fit, we always have a right-tailed chi-squared test. So based off of the fact that my chi-squared value was really quite low, I'm just going to guess, before I go any farther, that we are not going to be able to reject this because it was quite a low value. And since I only need right-tailed tests, we usually need relatively high values in order to be able to reject. But I don't get to just make that guess. What I need to do now is I need to go and find my critical value. So you would need to go to your chi-squared standard table. Now my degrees of freedom said I need to take my number of categories minus 1. Well, over here, I have 5 different categories, so 5 minus 1 is equal to 4. So my critical value from my table, when I go down to degrees of freedom of 4, ends up being 9.488. Okay, so now since my test statistic was lower than my critical value, so my critical value right here is 9.488. Since my test statistic was smaller than that, I cannot reject my null hypothesis. And now remember, my null hypothesis was that all the categories are equal. So I cannot reject that statement. I don't have evidence to say that, one of the categories is different.